Preview, right? All right.
All right, it's recording.
Okay. If you guys want to turn your video on, that would be wonderful because I can see you while I'm talking to you. So this way you can raise your hand so I can see you, or if you want to say something, or if you have any questions. So today's session is going to be, I think we have an exam coming up, right? We have an, just a minute. I think there are some more people joining the class now. All right. Okay, great. Just give 1 minute. Well, guys, so if you want to turn the video on, you're more than welcome. That would be nice so I can see you while we're talking. Unless you're not in a position to turn your video on, that's okay, but it would be nice to have that. All right. Thank you, Sam. Thank you, Mike. Great. Today, we're going to review the material that we have been going over for the past 4 weeks. We have been going through a lot of stuff, a lot of derivations, a lot of math, a lot of concepts. So the exam, again to repeat, will have 25 multiple choice questions, and you will be having plenty of time, much more than what you would have in a classroom. All right, and you will have 2 full days to complete the exam, but once you start the exam, you should try to finish it in one sitting. I think you will be given 90 minutes or 120 minutes, depending on how it turns out. So you'll have plenty of time. You're allowed to keep a periodic table next to you, have a calculator, and make sure that you have a stable internet connection. That is extremely critical, because without that, what happens is when you start the exam, and if you have a not so reliable network connection at home, I would advise that you try to come to the campus. There are many spots that have good Wi-Fi connection on the campus, so you can come and do the stuff. So today what I will do is, I'd like to tell you the topics that will be covered in the exam. A lot of you are asking whether molecular orbital theory that we discussed last time will be on the exam. The answer is no. Molecular orbital theory will not be on the exam. The exam will be from the beginning, whatever we have been talking about, the nuclear chemistries, nuclear transformations, types of nuclear reactions, stability of the nuclides, and how to predict the products of a nuclear process, how to calculate the binding energies of the nucleus. If you go back, we have done quite a lot of stuff in that area. So those are all some questions, and there will be some on the atomic structure, including the electronic configurations, the angular momentums, the Slater's rules, the effective nuclear charge, and meanings and exceptions to a variety of principles, such as the size variations, the ionization energy variations, the electron affinity variations, and electron negativity variations across the periodic table. With exceptions, noting, of course, you should also know what the exceptions might be, okay, and why the exceptions are. So more than half of the exam, I would say, is conceptual. That means I will throw at you a bunch of statements, and I want you to pick up the one that makes most sense. Okay. Similarly, when you have a numerical problem, it is important to recognize that your numerical problem, the answer should be the closest one. See, what happens when you're doing the calculations is some of you may be taking the coefficients or the constants to less number of significant figures, in which case your answer may be slightly off from the actual answer. So the rule here is always pick the best possible answer, whatever is the closest to the thing. It will never be exact, because different people take constants to different number of significant figures. For example, if you are talking about Planck's constant, right? So sometimes people will put 6.6, sometimes people put 6.3. Sometimes people put 6.626 times 10 to the negative 34. So depending on what you pick, your answer will be truncated to that number of significant figures. So it's always good to see what is the closest answer that you're getting. So don't complain that I don't see a choice that my calculator display shows. All right. I think you know this already, but I don't want you to get frustrated about this. Am I clear about this? Okay, and the valence bond theory that we talked about will be part of the exam. The Vesper theory, the geometries of molecules, the states of hybridization, all the stuff we went through will be part of the exam. Additionally, we will also talk a little bit about the bond energies, bond strengths, bond orders, the concept of resonance. So if you go back and look at all the stuff we've been doing quite a lot of stuff in just 3-4 weeks. We have covered quite a good ground. So I would like to use this session not to introduce any new material and confuse you for the upcoming exam, but rather take any questions you may have or any concept that you want me to go over it again one more time, just to make sure that you all understand it properly. So I'll take the questions from the floor now. Any questions?
I have a question.
Sure.
So I don't know if this will be important or not, but like on one of the slides, there was a graph of atomic number on the x-axis and electronegativity on the y, and it was showing that the noble gases had the highest electronegativities, and that didn't make sense to me.
In fact, we don't worry about noble gases. The reason is they are not chemically active.
Okay.
So for example, if you look at helium, neon, argon, krypton, xenon, radon, right? These are all the noble gases. Electronegativity makes no sense to them because electronegativity comes into picture only if an atom binds with a different atom, right? That is when we look at the electronegativity difference, and that difference tells us the nature of the chemical bond. If the difference in the electronegativity is less than 0.5, then we say it's purely covalent. If it is between 0.5 to 1.7, we say it is polar covalent. And if the difference exceeds 1.7, then we know that bond should be classified as an ionic bond. But none of this applies to inert gases because they don't make any compounds under normal circumstances. That answer your question, Mike?
Yeah.
I have another question.
Yes.
So can you go over the hardness and softness again? I know it depends on the size. So a small atom is gonna be harder because it's gonna have a more spherical shape. A larger one, it's gonna be more. It's not gonna have a spherical shape. It's gonna be kind of. It's not gonna be symmetrical.
You're correct.
I didn't understand the math behind it, like the coefficient when you.
Okay. Conceptually, you're correct, Gurveer. The hardness or softness is related to how polarizable the molecule is or how polarizing the molecule is. Watch my words very carefully. You see, I'm using two words, polarizing and polarizable, right? Well, what is the difference? Small atoms are very difficult for us to externally polarize them. By putting an electric stimuli, you will not be able to polarize a small molecule as opposed to a large atom, which is easily polarizable, right? So when you bring a very small atom close to a very big atom, the small atom polarizes the more easily polarizable large atom. Okay? For example, if I bring lithium to tellurium, lithium is a very small atom, it's very hard, and when you bring close to tellurium, it distorts the electronic cloud around the tellurium atom, and the tellurium atom loses its sphericity. It is not spherical anymore, it gets like distorted. I think the example I gave you was on the soap bubbles. The smaller bubbles tend to be more spherical, the larger bubbles tend to be lopsided, right? So that distortion from the spherical symmetry gives you what we call an internal separation of charges, the positive and negative within the atom. Okay, that is what we call the instant dipole formation. Now, coming to the mathematical aspects of it, the hardness of an atom is defined by, I'm going to write it here, is 1/2 of the difference in the ionization energy and the electron affinity. If you can see that one there on the board. Okay, so as you know, smaller atoms have very high ionization energies, right? So generally small atoms tend to be very hard. So that is a factor that people use, that is a number people use to indicate how hard an atom is. Keep in mind that electron affinities are very small for any atom for that matter compared to the ionization energies. So although technically we are saying the difference in the ionization energy and electron affinity, since the electron affinity is such a small number, for all practical purposes, you can say that hardness is 1/2 of the ionization energy. So atoms that have very high ionization energies, which are on the top of the periodic table, right? And which tend to be very small, are hard. On the other hand, atoms that have very small ionization energies, as you know, as you go down the group, right, the ionization energy decreases, right? So the hardness also decreases as you go down the atom. Am I making sense? I think I gave you
Yes.
more detailed stuff, both the math and the concept. Thank you for asking.
How is the coefficient used? Like, is that just a number, or is it applied?
It is applied in a lot of detailed calculations. For example, if you want to find out the diffusion coefficients of ions, right? So the hardness of the ion also comes into the picture. But we're not working on that, but this is a concept that we are learning that can be applied in advanced chemistries.
Thank you.
Thank you. Other issues? So how many of you have reviewed the material already from beginning to the end? Those of you who don't have a camera on, I don't know whether you have done it or not.
I haven't made it all the way to the end, but getting there.
I know, but don't postpone this. What happens is this material, when you look at it, it looks very smooth, but when you want to apply the material to the exams, you need to have a very thorough understanding of it. And you have to be very careful, read the questions. Sometimes people answer wrong because they did not read the question properly. Okay? So it's important that you must read the question properly. Don't come back and ask me to give you a partial credit just because you didn't have the time to read the question properly. Oftentimes people tell me, I know exactly how to do this one. It's just that I thought it's a 3p electron. I didn't know that it is a 5p electron that you're asking. That is not an excuse. All right, this is the first time I'm writing the exam on a canvas. I've never done that in my life. So if those of you are attempting early, if you find any glitches or if you have any issues, please email me. Okay. Once an email is sent, then I can put that in the announcements. I can tell you there may be an issue with one question. I try to do my best. Sometimes when you see a nuclide symbol, right? What I found out is in Canvas, there is no way of incorporating a symbol with the atomic number on the left-hand side lower corner and the atomic weight on the left-hand side top corner. So what I have done instead is, for example, if I want to write 238 uranium 92, what I will just do is 238 uranium. So when you see 238 uranium, because atomic number of uranium is easily accessed from the periodic table, you can write that as uranium 238 on the top left-hand corner and the bottom 92. Am I clear? Is that clear to all of you? All right.
I have
So,
another question, Professor.
sure.
So, you know the group 6 that has chromium and tungsten, and also the group of 11 which has copper, silver, and gold?
You're missing one element. You're
Uh,
missing one element, chromium, molybdenum, and tungsten.
yes.
Okay, yeah, go ahead.
And that group and group 11, so they have one electron. The 4s electron, the 4s doesn't get filled before, and it jumps to the 3d shell, right? Before it fills up the 4s electron.
Well, Gurveer, I think we have to make a small correction here. For the chromium, right, it is argon and then 4s1 3d5. That's an anomaly.
Yes.
There is no f orbital there. It's only between s and the 3d.
No, I said sorry, did I say yes? I said 4s and 3d.
Correct, yes.
So it doesn't fill the two electrons don't go in the 4s shell. One of them goes into the 3d.
Yes.
And why does that happens? Because the 3d shell is more stable, right?
No. Here is the point. When you have a half-filled shell or a completely filled shell, the orbitals get extra stabilized because there is a lot of exchange correlation that can happen. So when you have 3d5, right? So you have 5 unpaired electrons in 5 orbitals of the 3d subshell. Listen to me carefully the way I'm saying, 3d subshell and orbitals, right? Okay, so when you have 5 unpaired electrons in 5 orbitals of the 3d shell, that shell gets stabilized because it's half filled. All right. And similarly for the copper, right? You expect the electronic configuration to be argon 3d9 4s2. But if you look at 3d9, it is 1 electron short of getting completely filled. So completely filled and half filled shells assume unusual stability. And for that reason, what they do is they borrow an electron from the 4s and bring it to the 3d. That happens only in 2 cases, chromium and copper. But if you look at the elements down below, tungsten and molybdenum, those things are a little bit more tricky. I will give you an example. Suppose if you have vanadium, what should be the electronic configuration of vanadium? Argon 4s2 3d3, right? Yeah, that's what it's supposed to be, vanadium, right? So it is a D3s2 system. When you go to the element below vanadium, which is niobium, you also expect 4d3 5s2. But that's not what happens in niobium. In niobium is an anomaly. So it becomes 4d4 5s1. So these anomalies, that's why I feel it's a crime to put all the elements in a periodic table, assuming that every element in the group behaves the same. The more you know about the elements, the more you know about inorganic chemistry, you will appreciate why is it such a big crime to put the elements in a periodic table and then log them up. You would expect sodium and lithium to behave similar, right? Because they're in the same group. Yeah, but you know the reality? Lithium hates sodium. We still don't know why. You cannot mix sodium and lithium. They're chemically very similar, but still each element has its own personality, just like all of us were different, right? Yeah, there are some trends that are common. Yes, it's true that all of us have 2 eyes, 2 ears, 2 hands, 2 legs. Yeah, but that doesn't mean that we're all equal. So there are similarities and there are exceptions. Okay? But for the chromium and copper, we know the reasons why this happens. But when you go to the other elements, we still do not have a good understanding, even now. But we know the facts now that we did not know before. We don't know the reasons, but we know the observations. Okay, other questions? You all had paid the tuition, right? Or is it that Gurveer is the only one who paid the tuition and the rest of you are taking a free ride? You know, you can ask questions too.
Professor Chari,
Yes,
can we do a valence bond theory example?
of what?
Like ones from your lectures were like O2, like things like that. Let's see.
O2 does not have valence bond thing.
Or
Valence bond theory applies only to molecules that have central atoms.
trying
It's
to
good
find
to
an
know that.
example.
Yes.
Oh, we did them of you did one of like PF5 NO3 minus.
Correct.
Could we do an example of like a valence bond theory type of setup?
Yeah, like for example, if I ask you, what is the state of hybridization of nitrogen in, let's say, pick up a molecule like HNO2, okay? Can you all see HNO2? Right? Suppose if I ask you what are the angles, what are the geometries, what is the Lewis structure, what's the state of hybridization, how many central atoms it has, and what is the state of hybridization of all the central atoms. How do we do this? You got to start with a
Lewis structure.
probable Lewis structure. You are absolutely correct, Elisa. So what should be the Lewis structure look like in this case?
Nitrogen has to be in the center.
Because?
Isn't it because it's the most electronegative atom?
No, just the opposite. It's the least electronegative.
Least, okay.
So the least electronegative atom tends to be the central atom, right? Okay, so if that is the case, can I just say the structure is something like NOOH?
No.
No.
The oxygens need like 2 bonds, and the nitrogen needs 5.
Nitrogen needs 3 bonds, but oxygens, of course, need 2 bonds, right? And 8 electrons around them. So what's the probable Lewis structure? What is this molecule called?
Is that nitric acid?
Nitric
Not,
acid.
right?
It is not nitric acid, unfortunately.
Nitrous acid.
Huh?
Nitrous acid.
You're absolutely correct. Nitrous acid. Because it's a nitrite anion, right? So when it is an acid, where would the hydrogen go? Generally, in all oxy acids, the rule is there is at least 1 OH bond, right? Elisa, do you agree with me?
Yeah, I think it would be on one of the oxygens.
It has to be, right? Because all oxy acids have hydrogen bond to oxygen. So we have to now start with a Lewis structure where you have NO. Can I have this?
No.
No.
Because
Nitrogen only has one bond there.
there are no oxygen-oxygen bonds in molecules that contain more than one oxygen unless otherwise specified. The specification will come in the form of ozonides, superoxides, or peroxides. This is neither a peroxide, nor a superoxide, nor a ozonide. So you cannot have a direct OO bonding. So the only way you can write this is NOH and another O here. Remember all these rules, right? I mean, if you make a mistake in writing the electronic configuration, then you get the rest of these things wrong. So once you complete the Lewis diagram, that's what the structure looks like. Hannah, is this acceptable to you?
Yeah, thank you.
Okay, the next thing is, what's the state of hybridization on this nitrogen?
sp2.
How do we get this?
I just count the number of bonds it makes. So the first one has to be S and then the 2 P's. So that's how I remember it.
All right, a simple way of doing this is to count the number of atoms connected to the central atom and add the number of lone pairs on the central atom. As you can see, this one has 2 atoms connected to it and 1 lone pair. So the steric number on this atom is 3. So which means you need to have 3 hybrid orbitals. So that implies that you need to combine 1 s and 2 p's, right? The number of hybrid orbitals you get is exactly the number of atomic orbitals that you mix. So if you mix 1 s and 2 p's, you get an sp2 hybridization. That is how we know it is sp2. And what should be the geometry around the nitrogen? The electronic and molecular geometries.
Planar?
Is it linear?
No, it's a planar.
What planar? Is it square planar?
Trigonal planar.
So it's very important to qualify it, right? Planar
Got it.
can be square or it could be trigonal planar. So it's a trigonal planar structure. So if it is a trigonal planar, what is the expected geometry around this?
You mean angle? Is that what you meant?
Yes,
120. If it's trigonal planar.
that's correct. So this angle O and O bond should be 120. Do you expect it to be perfect 120 or do you expect to see any deviations?
There's a deviation.
The reason for that is?
Electronegative atom, because of oxygen, I think.
No.
I think it's the lone pair that is pushing down the bond.
There are 2 things that are going on here. Number 1 is the lone pair is free to go anywhere because it's not bonded. So this will apply some torque, but then there is also a repulsion between bonded electrons here because there are 4 of them here, there are 2 of them there, right? So there are 2 opposing factors. So depending on which one wins, the angle can be more or less than 120 degrees. And that is the case. So we do not expect this to have an ideal 120 degree bond angle. So the next question, suppose if I ask you the bond angle between nitrogen, oxygen, and hydrogen, what should be that angle close to? Ideal and any deviation?
104.5.
Ideal. Where do we get 104.5? What's the geometry around oxygen there? The electronic geometry around oxygen, what is it?
Which oxygen?
10.
It's oxygen here.
That one? Okay.
That
How many atoms it is connected to? 2 atoms?
2, and
There
then
are two lone pairs, right? So the total makes it
sp3.
4. So sp3. So the ideal bond angle there should be 109 degrees.
Yeah, 109.5.
109.5. Because you have two lone pairs here, right? These lone pairs will apply torque on this bond and make this angle less than 109 degrees. Hannah, am I clear here?
Yes, you are. Thank you.
Good. So all the results and the answers that we are providing to these questions comes from valence bond theory. Orbital mixing, the geometries, the Vesper theory, the VBT. We are not openly discussing this, but this is all the background that helps us to predict the bond angles.
Professor, could you explain me why the oxygen attached with hydrogen doesn't have 8 electrons? Oh, sorry,
As-
it does.
It does, yes. There are 2 bonded electrons and 2 non-bonded electrons, right? Makes it 8.
Sorry, I had a quick question.
Yes.
So, because molecular orbital theory isn't on it, do we not have to worry about bonding and anti-bonding?
Correct.
Okay, just want to make sure.
Yes. The concept of bonding orbitals, anti-bonding, and non-bonding orbitals comes from molecular orbital descriptions. At VBT, we still need to know, for example, there's a double bond here, right? Can we characterize how many sigma bonds and how many pi bonds we have in this molecule? How many sigma bonds and how many pi's?
Yeah, we can.
Yes, and how many sigmas and how many pi's?
3 sigma, 1
3
pi.
sigma, 1
3
pi.
sigma, 1 pi.
3 sigmas and 1 pi, all right? Suppose if you look at the pi bond here, what orbitals, if any, are involved in the formation of this pi bond?
Can you repeat the question?
What orbitals are involved in the formation of a pi bond there? Is it s orbitals, p orbitals, d orbitals? What is involved here?
The p orbitals?
P orbitals, you're correct. Which p orbitals? Can I say this pi is px of oxygen and py of nitrogen?
No.
Because
Because
px and
they have to
py,
They have to be in the same plane, so they'll both have to be px.
for you to have a lateral overlap, which is what is required for a pi bond, you need to have the orbitals in the same orientation. You cannot have 2 p orbitals which are normal to each other making a bond. So if it is a px of oxygen, it better be a px of nitrogen. Or if it is a py of oxygen, again, xy is the designations are arbitrary, right? If one is x, then you can call anything x, y, or z. So you should be able to identify. Suppose if I ask you, what orbitals are involved in the sigma bond between the nitrogen and the oxygen that is bonded to hydrogen?
It has
What is that sigma bond? Sigma what?
sigma. Is it S, and then if you want the perfect, then I would say SX, SX.
Sx, there is no Sx, only Px is available, sir.
Yeah, I mean, but since you want, then I don't know.
These are all the
Is it
consequences
just
of
2 s orbitals?
No. What's the state of hybridization of this nitrogen? What did we say it is?
sp2,
What did we say the hybridization of the oxygen is?
sp3.
So when you have a sigma bond between nitrogen and oxygen, what orbitals are involved then?
S.
the sp2 of nitrogen and sp3 of oxygen. You see, just with one molecule, we can ask thousands of questions, all related to the valence bond theory. Geometries, hybridizations, bond angles, nature of the chemical bond, shapes. That's how much you can get just by looking at one Lewis structure. That's the beauty of Linus Pauling.
Sorry, when with the pi bond, is that what we said? Did we say it was px or?
It could be anything. It
Oh,
cannot
okay.
be px and py. If it is pz, fine with me. Py, fine with me. But don't write pz.
It can't be different planes.
Different. See, what happens is when you have mutually orthogonal orbitals, right? Right? You cannot have a bond between, let me say, I have my middle finger on my left hand, okay? And my thumb here, right? They are normal to each other. There is no overlap. Because this px, if you call that px, attacks the py at a spot where there are no electrons because there is a node on my thumb here, right there. So it has to be in the same plane. So for example, if you have a sigma bond here, I can have two middle fingers or two thumbs. But you can't have a thumb and a middle finger or index finger. Okay, it kind of gives you a visual picture of how the overlap happens. It's a lateral overlap. You need to have the wave functions also in phase. For example, if you have a px bond, then you need to have the px orbitals with the same geometry. Can you see the p orbitals here? Plus and plus here. If this is plus and if this is minus, tough luck. You're not going to have an overlap there because they are out of phase. So the wave functions have to be in phase for them to laterally overlap. These are not bonding orbitals or anti-bonding orbitals. This is the symmetry of interaction.
I had a question real quick.
Sure.
So, along with the valence bond theory, there's like the coefficients in front of the wave function. So it was like the 1 over square root of 3, 1 over square root of x6. Sorry. Do we need to know that?
You don't need to memorize them, but if there is a
Okay.
question, you need to understand 2 or 3 important things. Number one is, if I have, let's say if I'm dealing with sp2 hybridization, right? sp2, how many hybrid orbitals we have? Hannah, I cannot hear you.
3 is sp2, so
3,
maybe 3.
yes. So you will have 3 wave functions, right? Chi1, Chi2, and Chi3. When you write these wave functions, it should be such that if you take an integral of Chi1 and Chi2, it should be 0. Or similarly, Chi2 and Chi3 should be 0. Chi1 and Chi3 should be 0. However, if you take Chi1 and Chi1, that should be 1. So that is how we choose the coefficients to make sure that we follow the orthogonality rules. Okay? Those 1 over square root to 1 over square root 3 are normalization coefficients, they call them. They just make sure that we have the integral of 2 different wave functions 0 and the same one 1. The other thing is, even within the wave function, let's say if I have 1 over square root 2 of atomic wave function of 1s plus 1 over square root 3 of atomic wave function of the p orbital, whatever it is, when you take these coefficients, square them and add them within the same wave function, it should be 1. The third thing is, when you take the coefficients of the same orbital in the different wave functions, when you square them and add, it should work out to 1. So these are the 3 conditions. That is how you know whether it's a valid wave function or an invalid wave function. Am I clear?
Yeah, so with that, so going like this way and this way should equal 1
Correct.
on the sides. Okay.
Yes. And they should be orthogonal to each other. Does that make sense?
Yes, it does.
Great. Excellent.
With the first, like the first videos you posted, like during the first week of school with the nuclear fusion, fission,
Mhm.
reactions like that, that's also part of the exam, right?
That's correct.
Okay.
You should be able to identify the types of nuclear reactions, be able to predict the products of the nuclear reactions, be able to calculate the binding energies of the nuclear processes, and also be able to calculate the binding energy per nucleon of any given nuclear process. And be able to understand what is fusion, what is fission, and why iron is very stable. What type of nucleides are stable? We talked about that too, right? Nucleides that have even number of protons and even number of neutrons are more stable than the ones that have odds. The least stable nucleides are those that have odd number of neutrons and odd number of protons. Remember that stuff?
Isn't iron like the tipping point? Like that's the most stable, and after that it's like
Yes,
less stable.
correct. So what happens in iron is, that is where the binding energy per nucleon is highest. If you recall the slides that we talked about, if you look at the graph, it looks something similar to this. Elements left of iron have lower binding energy. So if you plot the binding energy per nucleon and the atomic number here, you get a graph that kind of stabilizes with the iron. All right, so what happens is elements on this side, like lithium, hydrogen, these things tend to fuse. In other words, they undergo nuclear fusion to make a stable iron nuclei. On the other hand, the nucleides whose atomic number is greater than iron tend to dissociate the nuclei to make iron. So the driving force for fission on the higher atomic number and fusion at the lower atomic number is because of the unusual stability of iron. Does that make sense to you? Just as we were talking yesterday, there was a study conducted to see if they can have a mini nuclear fusion reactor, and they found that design is good. So maybe 10, 20 years down the line, we will have portable nuclear fusion reactors. It's almost like having a sun in your home. That will be enough, right? For you to power up all the house needs, electronic needs, electrical needs. If, you know, that is what we are hoping for. Maybe 40, 50 years down the line, every home will have what we call a baby sun, a mini sun, small one. And as you know, sun gives off energy. The energy that you get from sun in one day is enough for about 10 years. Imagine bringing the sun into your home. You may not see this in the mainstream media. So you need to be reading scientific journals, which is what I do every day morning to teach myself what is happening in my community now. Every year.
Hey, Professor?
Yes.
Oh, I'm sorry, I had a question.
Sure, Trevor, go ahead.
So, well, before I ask that question, does that say, like on that graph, is that electron affinity, like on the left side? Is that like...
No, this is binding energy per nucleon.
Oh, binding. Okay.
Be.
Okay. Can you do that? Can you review like the trends, like on the, you know what I mean, like on the periodic table, like the trends and stuff?
Which trend? Pick up the property, then we can talk.
I know electronegativity, like so electron affinity, like we have to know like that, like across the periodic table.
Yeah, I mean, you don't need to memorize all the numbers, numerical numbers, but we need to know the trends, right? So
Oh yeah, the trend. Yeah.
which one you are interested in, electron affinity or electronegativity?
Electron affinity, really.
Okay,
I always get
electron
them
affinity.
ionization energy, because like I get them like mixed up sometimes, like a lot.
Okay,
Yeah.
so to remove any confusion, let's talk one at a time. Let's talk about electron affinity. Electron affinity in general increases from left to right and decreases down the group. Keep in mind that all atoms like electrons, but the electron affinity is basically in this trend here. All right, the next thing is, while this trend is 95% accurate, there are some exceptions. For example, if you look at lithium and the next atom is beryllium, right? If you look at the periodic table, so which one should have higher electron affinity?
Lithium. Sorry, beryllium.
When you go from left to right, you would expect increase in the electron affinity, right? But then experiments tell us that beryllium has an electron affinity lower than lithium. How do you explain this? What's the most probable reason for this observation? Every time you encounter an anomaly, what's the thing you need to do?
Electronic configuration.
Write down the electronic configurations and see anything funny happening here. If you look at lithium, right, it is 2s1, 1s2, 2s1. In the case of beryllium, it is 1s2, 2s2. So when you give an electron to beryllium, where would that electron go? The extra electron, is there any space in the 2s subshell? No, so it has to go to the 2p subshell. When you go to the p subshell has an angular momentum, right? Higher the angular momentum, the more the electrons tend to stay away from the nucleus. So in other words, they are not highly stabilized. For that reason, the beryllium does not like to add an extra electron, right? So that is an anomaly. It's really not an anomaly if you really understand the electronic configurations. Similarly, if you go to boron to carbon, which one should have higher electron affinity? As per the trends, what do you expect?
Don't you expect it to be carbon?
You are absolutely correct. In fact, it is the case. Carbon has higher electron affinity than boron. So how about nitrogen next to carbon?
You would expect it to be more as well.
Should be expected to be more as well. But then observations show that's not the case. Nitrogen again is an anomaly. Why? Here again, we write the electronic configurations, 1s2, 2s2, 2p3. In 2p3, we have 3 electrons, half-filled 2p shell, right? When you give an electron, where would that electron go?
In the first, I guess, box, and
in one of the p orbitals, right? In one of the px orbitals. So when you do that, when you put an electron here, you're doing two things. One is 3 electrons in 3 orbitals, half-filled, are extremely stable. And then when you put an additional electron, you remove that stability. The second thing is you're also introducing electron-electron repulsions in the nitrogen 2p subshell. So that electron is not welcome. So nitrogen does not want to add an electron because it disturbs the stability of that atom. That's the reason why there is an anomaly. But when you go from nitrogen to oxygen, there are no anomalies. Right? Oxygen has more electron affinity. And then if you go to fluorine, fluorine has more electron affinity than oxygen. So the only deviations that you see are in the case of beryllium and the nitrogen in the second period. So when you go down the group, sulfur, selenium, and tellurium, what should happen to the electron affinity?
It should increase.
Increase or decrease?
Shouldn't it increase?
What did we say here as go down? They decrease, right?
Oh, it decreased. I'm sorry. Never mind. It decreases.
So tellurium should have smaller electron affinity compared to the head atom oxygen, which is true. Similarly, if you look at carbon and silicon, germanium, tin, and lead, for example, right? Carbon, silicon, germanium, tin, and lead. What should happen to the electron affinity? Should decrease. Decrease, you are correct, absolutely correct. Similarly, if you go to fluorine, chlorine, bromine, and iodine, what should happen to the electron affinity as you go down the group?
It is expected to be decreased, but I don't think that that's the case.
Because we talked about this, right?
Yeah.
You would expect chlorine to have smaller electron affinity compared to fluorine, but unfortunately, chlorine has a slightly higher electron affinity than fluorine. Why is that the case?
Smaller size of fluorine.
No, yeah, smaller size. And what is the implication of smaller size? If size is the consideration, that should also apply here too, right? Carbon, silicon too.
Small size.
Chlorine has more protons.
That should apply here too, sulfur. Whenever we present a logic, right, we have to make sure that it is convincing enough that. So again, we got to go back to the electronic configurations. In the case of fluorine, we have 1s2, 2s2, 2p5, right? That's the second shell. It's very small. It's already crowded with 7 electrons in that 2-second shell. And when you add an electron to the 2p, you are crowding that even more, and there are huge electron-electron repulsions. But when you go to chlorine, it's a 3s2, 3p5. The third shell has more space, and it also has an empty 3d orbital, which fluorine does not have. So adding an electron to chlorine stabilizes the structure. So chlorine has more electron affinity than fluorine. That is an exception. So we talked about the general trends, and we also talked about the exceptions. Trevor, does that make sense to you?
Yeah, that was good.
Good. So we know the general trends, we know where the
Professor?
exceptions are. Yes.
Could we can we go over back to Lewis structure? Can you draw Lewis structure of NO3 negative?
Sure.
I'm just getting confused. Where should I put the negative charge?
The negative charge is delocalized.
So just
So here, when you look at the formal charges, right, of this Lewis structure, the formal charge on this oxygen is negative
negative
1.
negative
This is
1,
negative 1.
plus
This is
1.
plus 1. And this is 0.
0,
Okay, so they come, if you add all the formal charges, it becomes
negative 1.
negative 1. So that negative 1 does not stay on this oxygen or this oxygen. It is delocalized on all 3 oxygens. In other words, this is not a double bond or this is not a single bond. This double bond rotates between 3 oxygen atoms. So here is a case, we have 3 atoms and 4 bonds, correct?
Yeah.
So this is a resonating structure. So the bond order is not exactly 1, 1, and 2. Each bond order is 4/3, that is 1.33. So this is not a single bond. It is more than a single bond. That is not exactly a double bond. That is less than a double bond. So on average, the bond order is 1.33. So when you have 3 bonds with a bond order of 1.33, the total bond order is going to be 4, which is what we have, 2 single bonds and 2 double bonds. So the placement of the multiple bond within the NO3 minus structure leads to different possibilities. Those are called canonical structures or resonating structures. And we said resonance gives stability to the molecule, right?
True.
Hmm?
Yes.
Without
true.
resonance, suppose if I were to add a hydrogen to this. So how many resonating structures now we have? Can I place the double bond here now?
No.
I cannot, because the oxygen is already having 2 bonds, right? So this double bond can only be altered between these 2. So the number of resonating structures are reduced when I add a proton. So what the molecule tries to do is it wants to be very stable. So what this does basically is it breaks this proton and give you NO3 minus. Does it explain now why nitric acid is a strong acid?
Yes. Because of resonance. Delocalize.
Because when you deprotonate the acid, you get an anion that is resonance stabilized.
At the conjugate base, it's more stable.
Correct.
All right. Thank you.
Sahil, did I answer your question?
Yeah. Thank you.
Good. Any other questions? If I don't hear, yes.
So when we're drawing the resonance structure as shown on the board, I know some teachers, instead of drawing like the dashed lines to indicate the electron stream, they want us to do arrows in between and like one structure for each like double bond on each O. On the exam, will you prefer the dotted lines?
In the exam, you will not be writing anything.
Yeah, so if we are given a choice, are we to be expecting the dotted line so we can practice just doing that?
See, there are not just one way of doing the Lewis structures.
Yeah.
Yeah, you sometimes write the next structure with a double bond on this side, right? And then single bonds there. So this is how you generate the 3 structures. The other way people do basically is they write That's another way of writing Lewis, the resonating structures. Okay. Writing a curve between the oxygens and the nitrogens that is telling you that there is a resonating structure.
Okay.
So, yeah. You will not get a choice that will be ambiguous. Okay.
Professor, I have a question.
Yes.
The inert perfect, it's only for lead, bismuth, and thallium, right?
What? The inert pair effect?
Yes.
Inert pair effect is more prominent in lead, thallium, and bismuth. But if you go up one element above, right, like if you look at the periodic table, you have indium above thallium, right? And you have a tin above lead, correct? And you have an antimony perhaps before bismuth. So even in tin, antimony, and indium, you still have the same effects.
Okay.
But they're not as prominent as they are for the elements down below.
Thank you.
Okay, great. If there are no other questions, then I wish you good luck with your exam. Next Monday, we will have another lecture on the molecular orbital theory, and we'll be starting the concept of symmetry, different symmetry elements and symbols, meanings, practicing, all that stuff. That's a good chapter. It requires a lot of
Chari,
imagination. Yes.
do you mean like you'll post a video, or you mean we're meeting on Monday?
We're not meeting on Monday. We will
Okay.
I'll be posting a video.
Okay.
Most likely in the MO theory and maybe symmetry part of it. We'll meet next Wednesday to go over some examples of symmetry. Okay. The symmetry requires a little bit of imagination, so we need to do lots of examples. Okay, folks. I wish you all good luck with your exams, and do it quiet. The night before you take the exam, have a good rest. There's no point in waking up till 3 o'clock in the morning and trying an exam at 7 o'clock in the morning. Yeah, that won't work. You need to have good rest. A lot of times, people don't do well in the exams, not because they don't know the material. It is just that you have not given enough rest to your mind. And a disturbed mind that is sleep deprived cannot function at its full efficiency.
Dr. Chari, I'm always like that, so I just work like that. Usual. My mind is always on that feeling of being sleep deprived, so that's my usual brain. And I feel like if I did get a full night of rest, I'd be more lazy and not as useful as if I did how I usually do with 2 hours of sleep.
Yeah, I mean, it basically resting the mind gives you good alertness. But that's my recommendation. I'm not asking that everyone sleep 10 hours before the exam day, which may or may not be possible. At least a good 8 hours sleep, you know, which is, it really makes a big difference.
I'd be lucky to get that much, but that's just me.
I mean, each one of us are different. Some people can work with 3 hours of sleep. For me, I need at least 8 hours of sleep before I recharge myself.
Sometimes I feel like I should give myself that much, but then I have like this thing in my mind where it's like I want to use as much time in the day. So I'm like, you know what? I'll just wait and stay up for a couple more hours.
I mean, as long as you're doing some useful work, it's okay. But you are staying up, watching a movie or playing a game or chatting with somebody, you know, that's...
No, not me.
Okay. I mean, there are some people who do this unproductive work, which cuts down on their actual time. You can work on the science, and they complain.
Yep.
I mean, you can't have both ways. You know, learning is hard. I mean, the university wants us to treat you all like customers, customer happiness. You know, in education, there is nothing like happiness. The happiness comes once you understand a material, really. So I don't call you guys as customers, but I would rather think of you all as the products of the university, not customers. Now, there's a big difference, right? Because when you go out, you bring name to the university. And if you do well, somebody will recognize, wow, Rowan is doing a great job. They're giving great students to the society. That's what we want to hear. Not to make you comfortable and then say, all right, you know, just learn about the names of the elements and then you'll pass the exam. That's so easy now for you. But once you go into the real world, you will be surprised how many people are so competent. And sometimes, you know, you may fail out compared to the competition out there. It's better that you work now hard and take it easy later on. Rather the other way around. Other way around is not acceptable. And I don't see you guys have any responsibilities beyond yourself, right? I mean, you don't have a mortgage to pay or a lot of stuff.
I have a son.
I know.
I have taxes to pay.
I know this little bit of things are there, but you know, like imagine I have 3 kids and a wife that stays home, and my home has still not been paid off. You know, I mean, those are all the responsibilities I have. So I have to work really hard to make the ends meet and make sure that all my bills are paid and my kids' expenses are also taken care of. You know, you have a small kid, right? Trevor, your kid may be small, so I would say
No, I don't really have a son. I don't really have a son.
Even if you have a kid, a small kid, right? Small kid, small problems. When you have a big kid, you have big problems. Anyways, that's just on a lighter side. Don't take it serious. I wish you all good luck with your exams. And between now and, you know, by October 3rd is when the exam opens. If you have any questions, feel free to send an email to me or ask for another Zoom meeting. All right? So enjoy the rest of the day, and we'll meet you next Wednesday. Thank you very much, Trevor.